Hi everybody, this is Ms. Bufford, and in this video we're going to talk about measurement. Your learning goals are to be able to make measurements with accuracy and precision, and to be able to determine what labware is most precise for a given measurement. In this video, the term precision refers to the number of digits that you can read for a measurement. The smaller and more numerous the divisions on a device are, the more digits it can report for a measurement, and the more precise and accurate a measurement taken with that device will be. Knowing this, it's easy to see that not all measuring devices are created equal. Some devices can measure things with a high level of precision, or where they can report lots of digits, while others not so much. No matter the device though, one thing that they all have in common is that they have limits. No measuring device, regardless of how precise it may be, is perfectly accurate. So let's find out why. Before we do some examples, I just wanted to mention a couple things about measurement that we need to keep in mind. It's always important to estimate one digit past the smallest readable mark on a device, and this last digit naturally will contain some uncertainty or some error just because of the fact that it is an estimation. And the second thing that we want to keep in mind is that if we're measuring an object that is not long enough to pass any of the divisions on our device, then we're really just making an estimate about that measurement or the length or whatever it is that we're measuring. And so when we do that, we only want to make sure to estimate one non-zero digit, and then if we need to, we can use zeros to show the place value of that non-zero digit. And if you're unsure about that last one still, we're going to do an example on the next page that will hopefully clear that up. So for this measurement, I have this 100 centimeter ruler, and if you notice, there are no smaller divisions than 100 centimeters on this ruler. So I'm trying to measure the length of this blue line up here, and it's shorter than the smallest division on this ruler, so I have to estimate the length of this. And the best way to do that is just to estimate one non-zero digit and then use zeros to hold that place value. So let's talk about how to do that. I'm going to estimate that it looks like the length of this blue line is about 20 centimeters. So I'm going to say it's 20 centimeters. Notice though that I am not saying 21 centimeters or 22 centimeters, because there's really nothing on here that's indicating anything in the ones place. There's no way for me to really tell that. And so the best, most accurate estimation that I can make is to say that that line is about 20 centimeters. All right, so on this second ruler, it's still 100 centimeters long, but notice now that I have divisions every 10 centimeters. And I can definitely see that the last readable mark is this 20 centimeter line. It's the last division that my blue line up here crosses. And so I can see that it extends on beyond that a little bit. And so I know that the length of this blue line is going to be between 20 centimeters and 30 centimeters, somewhere in there. And if I were to envision 10 more divisions in between there, then I could probably estimate that that might be, 3 centimeters. So 23 centimeters would be my my measurement here. That's what I would say. This last digit though, because it's an estimation, some of you might have thought, that looks like 22 centimeters or 24 centimeters. And so that estimated digit, that's why we always say it contains some uncertainty or some error, because we estimate it. And it's going to be different depending on who's doing the estimating. But I'm going to say 23 centimeters. So there's, in this number, now I have a value that's pretty certain, and I have an uncertain value, and that 3 in the ones place. All right, so now I have that same ruler, and I've taken little divisions, and I've added 10 divisions in between each of these larger divisions from the second ruler. So each one of these little tiny marks on this ruler represents 1 centimeter. And so now when I take a look at this, I can clearly see that the line crosses here at the 22 centimeter mark, and it still extends beyond that, but it doesn't quite reach 23 centimeters. It looks like it's about halfway between. So what I can say now because that looks like 22, and it's about halfway to the next one, so 22.5 centimeters. All right. And so now I have 2 certain digits and still 1 uncertain digit. And so you can see as we add divisions on our measuring device, our number is, we're able to report more of those digits with certainty, but we always will still have that last estimated digit that does contain some error. But it is an important digit. So let's talk a little bit more about uncertainty and error. So no measuring tool, no matter how precise it is capable of measuring without a degree of uncertainty. This means that no measuring tool is perfectly accurate. We can have tools that are precise and accurate enough for our purposes, but as we reach the limits of that tool's ability to accurately measure, we run out of those measuring or those divisions, then we enter that realm of uncertainty. And because this last digit in a measurement is always considered to be the digit of uncertainty, it always contains some error, then if we were to perform calculations with those numbers, then our calculations would contain error, and we need to have a way of controlling or limiting the amount of error or the influence of that error in our final answers. And so later in this unit, when we talk about significant digits, that's how we limit error in our calculations. All right. In chemistry, you're going to need to know how to do certain types of measurements. These are the most common. We're going to measure length, volume, temperature, and mass. And so now we're going to talk a little bit about those. All right, so measuring length. In this class, when we measure length, we're just going to use a metric ruler. So for right now, go ahead and pause the video and see if you can read the lengths of these green lines, and then unpause it and we will talk about them. All right, so this first one up here, we have this green line that it looks like the last readable mark here is at the 39. And if we take a look at our scale, I've got a 39 here, and the next number reported for that line over here is a 40, which means that each one of these little marks in between represents 0.1 or a tenth of a centimeter. And so I'm going to say that my last readable mark is that 39. So I'm going to go ahead and put 39. And then it doesn't quite reach the first tenths place. So for my tenths place, I'm going to have to put 0 because it doesn't quite go to that first one right here, okay? But the green line does extend beyond 39, so I have to account for that length the best I can. And so what I'm going to say is it looks like it's about halfway between 39 and 39.1, so it's going to be 39.05 centimeters. So that's going to be my estimation for that. And now let's see the second one. I've got the green line extends past 73, but the last readable mark, let's take a look at what these little lines in between mean. So I've got a 73 and a 74 here. So again, these are each representing a tenth or 0.1 centimeters. So I've got 73.1, 2, 3, 4. And so there it is, and it looks like it extends just a tiny bit past 73.4, but it doesn't quite go all the way to 73.5. So 73.4, and it's between 73.4 and 73.5, so I'm going to put a 5. 73.45 centimeters is my estimate for that. Okay, now let's talk about measuring the volume of a liquid. So the amount of liquid that we're measuring will dictate the device that's appropriate for your purpose or for whatever you're measuring. And there's a general rule of thumb that applies to measuring liquid in the lab. You want to choose a piece of equipment that will reasonably fit the amount of liquid that you need to measure. So you want something that's not too small or too large. And you also want to pick something that's going to give you the most precise measurement, so the most digits that you can get. When we're measuring very small volumes of liquid in the lab, we'll generally either use some kind of pipette or a burette. If you look at this picture over here to the left, we've got a bunch of different types of pipettes that you might find in a lab. Some of these are good for measuring and some of them aren't. For example, this right here doesn't have any divisions on it, Neither does this one right here. Sometimes you can find these plastic pipettes that have some little divisions on them, but sometimes the accuracy of those is questionable. Then we've got these more precise and more accurate types of pipettes up here. This one, for example, is really good at measuring very small volumes, like microliters small. And it's got a little dial up here. You spin the dial and you tell it exactly how many microliters you want. Then you compress the plunger at the top and it actually pulls up just the right amount, as long as it's calibrated. And then we've got this other type of pipette up here. Sometimes you can find these electronic pipettes, and those are handy as well. But then you have burettes, and this over here is a burette on the right side. And with a burette, you have to have it suspended using a little clamp and a ring stand in the lab. And what happens here is you fill the burette with liquid, and then the liquid drains out the bottom, but you can control how fast it drains with this little valve right here. And these are really good at measuring very tiny amounts of liquid and dispensing really tiny, accurate amounts of liquid. So you could get this out drop by drop and measure just very small amounts. For larger volumes of liquid, graduated cylinders tend to be the best option. Anything larger than 1 milliliter, usually, depending on your graduated cylinder, these are just the best for measuring the most precise amounts for larger volumes. When it comes to using beakers and Erlenmeyer flasks, these are handy in lab and they do have some markings on the sides, but they're generally not considered very accurate. So those markings are there just to kind of give you a general idea of how much liquid you have, but not really very accurate. And then you have volumetric flasks, which if you kind of look in this picture over here, we've got some volumetric flasks back here in the background. These only have one marking on them, and they're calibrated very specifically for that single volume, just so that we can use them to create solutions that have certain concentrations, or we could perform dilutions using volumetric flasks, but they only have a single volume, so you want whatever volume you're looking for. We don't usually use these to measure. They're usually used for making things. All right, so let's go ahead and practice reading volume on graduated cylinders. And go ahead and pause the video for just a minute and then make your best measurements of these 3 graduated cylinders. And when you come back, we will go ahead and talk about them. All right, for this first graduated cylinder, the orange one, we always want to remember that it's, when we read graduated cylinders, we want to read from the very bottom of that meniscus, so very bottom of that concave shape at the very top of our liquid. So I'm going to go ahead and say, first have to pay attention to the scale. So I have a 10 here, and the next number on the scale here is a 12. That means that 11 is right here. Okay, so I've got 10 milliliters, and that means that each one of these lines is 0.2. So 10.246, and it looks like that my meniscus is just slightly above that. And anytime we have a scale that goes up by 0.2, if the line falls in between that, then we just have to estimate the next one up. So the best I could say here would be 10.7 milliliters. All right. And for the second graduated cylinder, the red one, again, I'm reading from the bottom of this meniscus up here, and I'm looking at my scale. So I have 3 here and then 4 here, which means that each one of these marks in between represents 0.1 milliliter, so 1/10 of a milliliter. And so let's say 1, 2, 3, 4, 5, 0.5, so 3.5, 0.6, 0.7, so 3.7. And now since these are going up by 0.1, if I were to envision 10 more divisions in between there, then it looks like that might be 2. So 3.72 would be my estimate for that one, or my measurement for that one. And then this last yellow graduated cylinder, I've got a 7 here and an 8 here, so each one of these marks represents 0.1. And so I've got 7. And since it looks like the bottom of my meniscus does not quite reach the 7.1 mark, I'm going to go ahead and put a 0 here because it's not touching that. And then I do know that it extends beyond 7, but not quite so far. So if I envisioned 10 more divisions in between here, then I would say maybe 7.09 milliliters. All right, so those are the measurements I got, and I actually should have milliliters after all of these. We always want to include units on any measurement we take so that we know exactly what that number means. All right, so now let's talk about measuring temperature. So in science, we measure temperature using the Celsius scale usually. And if you have a device that's measuring in Fahrenheit, you're just going to have to convert those temperatures to Celsius. And then occasionally we'll also need to be able to measure temperature in a temperature scale called Kelvin that we'll learn more about later. Some digital devices have the capability of reporting temperature in Kelvin, but if not, it's a really easy calculation to convert between Celsius and Kelvin. So some different options that we have in the lab for measuring temperature. The most common ones that we have are these liquid or alcohol-filled glass thermometers. There are mercury thermometers. I don't believe that we have any at our school. But then we also have some metal thermometers. Something like this could be used for a crude temperature measurement. Then we also have electronic thermometers. So we have these thermometers, either they're hooked up to a computer or some smaller device. They have those little metal temperature probes. And then there's another type of thermometer that we could potentially use is an infrared thermometer. This just measures infrared radiation that's being radiated by something. So let's go ahead and practice measuring temperature. Like I said, we have mostly glass thermometers in our lab. So let's go ahead and practice measuring a glass thermometer. So pause the video and give this your best shot at measuring, and then we'll talk about it in just a minute. All right, so when we're measuring temperature on this thermometer, we're just reading how high up this red line goes, and it looks like it's going just beyond 38. And so let's figure out what each one of these lines in between represent. So I have 38 here, and 39 is the next number. So that means each division in here represents a tenth of a degree, and so 0.1. And so I know that the last readable mark on here, it actually looks like it's going to be 38.1 because I can actually read that that's right there on that line. So 38.1. And then I still, even if it looks like it's right on the line, I still have to remember to estimate that last digit. And if it looks like it's right there on that line, I'm just going to say 38.10. So that's going to be my measurement for that temperature. Okay? All right, thank you for watching Buffered Chemistry. Subscribe to my YouTube channel for more chemistry help.